More about what we're doing here at the Intel booth. Our next presentation is going to be application offloading with oneAPI. Coming from the Leibniz Supercomputing Center, it is Gerald Mathias. Let's give him a round of applause.
Yeah. Hi, thanks for a nice introduction. I'm Gerald Mathias. Leibniz Supercomputer Center is one of the leading supercomputing centers in Germany. We are part of the Gauss Center for Supercomputing. And we've been partnering with Intel for the last at least 7 years for our high-performance computing systems. So my group takes care of user support. We are organized in different labs for scientific communities. We have an Astro lab, a lab for CFD, for life science, biolab chemistry, and a geolab for seismic calculations, weather and climate forecast. My group mainly does mentoring of large-scale compute projects. We maintain the HPC software stack for our users. We run trainings and workshops and help users with troubleshooting, optimizing their codes for tickets that take weeks, months, or even longer times. So involvement in joint research projects. Important part is code porting and optimization, and this is something I want to present you for our systems. So our flagship system is SuperMUC-NG, still one of the largest CPU-based systems in the world. It was installed in 2018. We're still running it. It has 6,400 nodes, 300,000 cores. And just recently, we acquired a phase 2, an upgrade of the system with, it's clicked, with a smaller system of 240 nodes, containing Ponte Vecchio GPUs from Intel. So it's roughly 1,000 GPUs in that system. And of course, we had to get our user codes ready for this new architecture. So these are some of the startup codes we were looking into. So the SYCL code, looking at tsunamis and seismic ruptures. We had OpenGadget and DPEcho from the astrophysics community. HEMLB, so lattice-Boltzmann calculations for blood flow simulations. And of course, also a large community we have from life science with molecular dynamics codes. Here, AMBER and GROMACS. So these were the first codes we were looking into when ramping up the system. Today, I'm just going to talk about 2 of the codes. One was the DPEcho code, which is a general relativistic magneto-hydrodynamics code for astrophysics. So originally, the echo code was written for black hole accretion, to describe pulsars, wind nebulae, and neutron stars. The original code was based on MPI and OpenMP. We did a roofline modeling of the code, and it was clearly memory bound. And speed up with SIMD with a factor of 1.2 was rather poor. Yes? Yeah, so this was mainly the memory layout that was used in the code. So there was no really, the memory was not organized that you can really vectorize it good. So this was the initial start where our colleagues started working on the code. And on the left side, there's a scaling plot. So even within a node, OpenMP scaling was poor. So we see a saturation of the bandwidth, of the memory bandwidth, and beyond that, not really, additional cores do not really speed up the calculation. So we decided to take this code and have it as a target code for our new Ponte Vecchio-based cluster. And together with the help of the folks at Intel Germany, we were working on the code and were porting it to a SYCL implementation. So the original code was Fortran, F90, and we started to port it to C++ and parallelize it with SYCL. So writing the whole code around SYCL, we started with a first intensive compute kernel. So that was called Echo Slim. And we profit from the memory on device. So all simulation memory stays on the GPU and is not transferred back to the host system. So that was my colleague Salvatore and Alexander Purple from Intel doing that. And since at the time when we started the project, we did not have the hardware yet, we were starting out on a simple laptop to see if our approach was working. So the benchmark system is depicted on the left side. It's a plane wave setup with gravitational waves and the magneto-hydrodynamics. And in comparison, the rewriting from the original blue-lined Fortran code to the orange C++ implementation already yielded a speed up of a factor of 2. And even with a consumer-grade GPU, the SYCL offloading of the workload to the GPU gave an immense speed up, as you see with the green line. But as I said, this is consumer-grade hardware, so we were interested how will that look on a real HPC system. We did some weak scaling tests, increasing the number of voxels, the number of cells per task in our system, and scanned through. So the graph is a bit, I have to explain what is depicted there. So we have a logarithmic y-axis, and it shows the million cell updates per second per task. So for the GPUs we are looking at, it's how many cell updates are there per GPU. We used the SYCL code, compiled it for different platforms, so for AMD and NVIDIA, as well, of course, as for our Ponte Vecchios. And one sees that we have a rather smooth performance throughout different setups. And actually, in this case, our SYCL implementation on the Ponte Vecchios is outperforming the other hardware we were looking at. So for AMD, it was a bit older cards. For NVIDIA, we were looking at A100s. So this gave us confidence that the oneAPI computing platform paradigms are working well for us. And in a second project I want to show you is the outcomes of our benchmarking for molecular dynamics codes. So here we just look into the GROMACS code. Typical setups for molecular dynamics simulations are systems from 10,000 to 10 million atoms. And for GPU-based systems or accelerator-based systems, A typical setup would be that you run one simulation system on one accelerator, and you have some weak coupling between these images to speed up sampling and do other fancy stuff. So for us as a data center, it's interesting, what is the minimum workload we have to require for GPU to really make use of the full capacity of the hardware. So for that, we define a performance measure which is the simulation time you can reach within 1 day times the system size. So the larger the system, the less simulation you will acquire. But to really measure that, we have set up a series of benchmark systems that are homogeneously scalable from 8,000 atoms to up to 12 million atoms. So the idea is that we use a solution of ethanol in water. So 10% ethanol in water, commonly called white wine. And this is a setup that you can really scale all across, and you can smoothly investigate. So we were running tests for these different system sizes and scanning through that. So what I will show you are the single accelerator results for different hardware. So data center level GPUs from NVIDIA and AMD, and the Intel Ponte Vecchio. And important to say is that both AMD and Intel have a dual tile or dual chiplet hardware. That is, you effectively have two logical GPUs on one single piece of hardware. And the results we got were quite promising. So we scanned through from 8,000 atoms to 12 million atoms, and beyond about 250,000 atoms, our performance measure went to a steady state, so it leveled out. That means for these system sizes, you make full use of the GPU, of all the registers, of all the memory you have there. The dual tile approach gives you an edge over the single tile hardware of NVIDIA, since you can run twice as double the number of simulations there. And what was also quite impressive for us, that you can run a broad range of system sizes, so even really big systems on a single piece of hardware without losing efficiency. So currently we are in the ramp-up phase for user production. We are looking into a few other codes, mainly from quantum chemistry. One part is Open CPMD, where we take the DFT molecular dynamics code Carpinello and port it to Ponte Vecchios. We have a project with the CP2K code, where we're looking into large-scale computations in material science. The Athena++ code from astrophysics, which is based on the Cocos framework for parallelization, and the grid framework for lattice QCD by Peter Boyle. And all these programs are currently running on our hardware, and we're trying to optimize and scale out these applications. So I would like to thank you for your attention and the contributing people. So we are part of the Gauss Center for Supercomputing in Germany. So we operate on a European level as a supercomputing center there. We say thank you to the folks at the NHR Compute Center in Erlangen, which helped us with the benchmarking. And of course, our colleagues from Intel in Germany, stationed in Feldkirchen, who really gave us an edge with all these programming issues. And with that, thank you for your attention.
All right, we have some time for some questions if you wanted to ask any questions. All right.
Yeah, so thank you for the presentation. I'm curious about, have you tried executing combining GPUs from different vendors, or you only tested with specific vendors? So only with Intel GPUs, only with...
So we were focusing on data grade GPUs, since we need that for cooling, for powering. And there's currently these big three vendors, so Intel, AMD, and NVIDIA, as we see it. All hardware has its virtues, but we did not look into other hardware. So currently we are looking into newer versions of the hardware, different newer cards, but... Sorry?
I mean, like heterogeneous execution, so using at the same time GPUs from different vendors?
No, that's not interesting for us. So we try to run a homogeneous cluster that is complicated enough.
Okay.
Thank you.